Hi class, today we're going to talk about volume using the shell method. We have talked about before the this method, and so now we're going to approach the volume in a different approach. This is using the shell method. So let's begin. We're going to find the volume of a solid of revolution using the shell method. Then we're going to compare the use of the disk method versus the shell method. So what is the shell method? So if you want to think about it this way, in the disk method, we ended up using disks, a bunch of disks, and we added a million disks to find the volume. So we broke down the solid into a bunch of disks, and then we were able to add all those disks, and we were able to get the volume. Well, with the shell method, instead of using disk, what we're gonna be using, cylinders. And so with these cylinders, are gonna have a hole, but what's gonna happen is we're gonna create infinite cylinders or shells, and we're gonna add them all together. So let's observe the next example and how this is gonna apply. So on the next example, we're going to find the volume of the solid formed by revolving the region bounded by this given function and the x-axis. So here is the function right here, and is being bounded by that function and the x-axis, right? So those are those two. So we're trying to find this volume, the solid created by this shape and that has a rotation about the y-axis. So if you notice, what's happening is that this is being rotated. So if you think about it, it's almost sort of creating like a donut from the top, but without a hole. So what we're gonna do is we're gonna try to understand what does it mean to be a shell method. One thing you guys will notice sort of different is that versus this method, when the rotation axis was like this, we usually had discs going on or washers, and when we rotate them, we were having that wasn't that good one. So let's say like this, and like this, right? So we were having sort of like a washer, right? And we were adding all these washers up and down, right? Up and down. So this is a different approach. If you notice, that's not any longer what we have. What we have is going to have this little rectangle. So if you guys want to see it better, this is how it's going to look like. So here is the solid, right? This is a three-dimensional. If you guys want to think about it, a three-dimensional, like this. And so if you want to see here the shell is this sort of almost like a cylinder, but with a hole, right? There's a hole inside. So if you guys think about it, you can see the cylinder, but instead of having a filling, it has a hole. So I hope I did a good job here trying to give you guys a good picture of how this looks like. And the idea here is, and you can pause it here so you can visualize it. But the idea here is that we're gonna be adding another shell, and we're gonna rotate it again, right? And we're gonna get another piece of a volume, and we're gonna do it again, another shell, right? And then that gives another additional volume, and we're gonna do this infinitely many times, right? So we keep getting these shells, and we every time this goes like this, and we just get a bunch of shells. So the idea here is that we're gonna be adding a bunch of shells at the end of the day. So how do we find? So the important thing is, how do we find this shell, the first one, right? Let's think about how can we find this first one, and then we're connected to similar things we did with the disk method. So let's think about this for a second, right? We already know that if we look at the picture over here, the two-dimensional, in order for us to find this shell, we need to figure out what is the volume of this shell. What is the volume of this shell? If you guys can picture it, it's like a cylinder with a hole, right? Well, in order for us to find this cylinder, well, we know that as any cylinder has a volume of pi r squared times h. So you need h, the height, and you need the radius. But that's actually gonna give you a whole cylinder, right? So we don't want the whole thing, because what we're gonna do is we're gonna cut it off, right? We're gonna cut it off. So we're gonna have the shell is not a whole cylinder, it's just like a piece of it, right? So what's gonna happen is that what's gonna happen here is that what we're gonna do is we're gonna find the cylinder of the outer cylinder, the volume of the outer cylinder, and then subtract it by the volume of the inner cylinder. So think about it like this. So you got the whole cylinder, right? And then you're gonna subtract it by another cylinder that is inside. So if you subtract this region, right, the inside one, what's left behind? All the shell, just the shell. So we can think about that the volume of this shell will be the outer cylinder volume, the volume of the outer cylinder minus the volume of the inner cylinder. In other words, the hole. Well, we already know how what we're gonna call the radius of the bigger outer cylinder will be big R, and the one for the inner cylinder will be little r. So let's begin. All right. So first of all, how do we find the big r, the big radius, right? So from the beginning all the way to the outside. Well, what we have here is the middle of this rectangle, right? We're going to use this rectangle. The middle of this rectangle is going to be the location of this rectangle. This rectangle is going to be from 0 all the way to p of x, right? We're going to call this p of x, position, right? Sort of kind of like position, but in fact it's more like the distance, right? The distance from here to the axis of rotation, right? The distance from here to the axis of rotation. So I'm talking about distance, right? Not like the where this is located. We're not looking at the location, but in fact we're looking at the distance from here, right? This is the reason why I'm adding that special note is because it's gonna make sense at the end. All right, so that's the center, but the outside of this cylinder is actually a little bit further away, right? It's a little bit further away because this is the middle. So what we're gonna say is, if this is delta x, then and you're in the center, then you're gonna have to add delta x over 2. So we're gonna say the outer radius is going to be p, which is, it gets you to the middle, plus delta x over 2, right? And that will give you the extra distance, and now you're over here, and that tells you the big radius. Since we're talking about the radius right now, let's talk about the inner radius, right? What's the inner radius of this shell? Well, that would be this side of the if you look at this rectangle, that would be this side. So it'll be the inner radius. So if you try this again, p is in the middle, and if you want to get just to the left side, then you're gonna have to subtract pi x over 2. You're gonna have to subtract half of the distance, the width of this rectangle. So that will give you the inner radius. So we got everything we need. So, excuse me. So where we're gonna fill it in here. The big radius is going to be p plus delta x over 2 r square times h, right? The height. This is the volume of the outer cylinder, and then minus the volume of the inner cylinder, which has a radius of p minus delta x over 2. At this point, we're just gonna do some algebra. We're gonna expand this binomial. This gives us that. Here's your pi. Here's your h. Do the same thing here. Here's your pi, and then expand this binomial, and that gives you that. Here's your h over here. Then you're gonna distribute your pi and your h in here, right? You're gonna distribute it, and we're gonna expand this whole thing. Pi times p squared times h, right? That gives you that. Pi times p times delta x times h gives you that. Pi times the quantity delta x squared over 4 times h. That gives you that. Minus, and now you gotta distribute the negative along with the h. So negative pi times p squared times h gives you that. Negative times negative becomes positive. Pi times p delta x times h gives you that. Minus times positive gives you minus pi times h times delta x squared over 4 gives you that. And then you can see a few things are going to cancel. And then so you're left with this right here and this right there, which is what we call the difference of volume. And pretty much is just going to be double this, right? Because they're the same thing. So you end up just getting 2 pi times p times h times delta x. Well, that gives us this single little shell, right? The volume of this single little shell. If you guys think about it, is the sort of the orange, right, along with the shell, right? And so we just found one of them, but remember we gotta do this infinite many times, right? We're gonna do that infinite many times. We're gonna create a bunch of shells, right? A bunch of shells, and we're just gonna add all those shells, but these shells are gonna be so small. So sort of kind of like the idea when we describe the area or when we describe the volume of the disk. So what we're gonna say is we're gonna just use summation to find the volume of the solid. So if we approach this volume as the difference of the deltas becomes 0, so as this becomes very, very small, very thin, then you're pretty much just adding all those p's times h, right? And you're adding infinite of them. So you have your 2 pi right there. And so this ends up being the integral, the definite integral of 2 pi from a to b px hx dx. And where's the a and b? Well, a and b will be wherever this travels, right? Wherever this is bounded by, wherever delta x is bounded by. So a and b in this case, right? So therefore, we ended up getting this formula, right? And this is the formula that we're going to be using, pretty much, right? You already know what p of x means. That's the distance of your rectangle or your perspective to your rotation, and then also and h of x is going to be your height. So this is the formula about rotation about the y-axis bounded by a and b. So let's try this example now. Let's go ahead and find the volume using this new formula. It's the same problem. So what we're gonna say, well, we already know a few things. We know what is going to be p of x. What's p of x? Well, p of x is the distance from the rotation, from the axis of rotation to the position of your rectangle, right? So what is that going to be? Well, if this is 0 and this is going to be at x, so it looks like p of x is x, right? It's going to be x. So if this rectangle is at 2, then you're at 0 to 2, so that will be 2, right? So it depends on what x equals to, right? your height in this case is going to be the height of the rectangle can be defined by the graph, the function given to you. So we put it all together. We already know, we're going to add a few notes here. We know that P of x is x, h of x is the height of the rectangle is going to be x minus x cubed. And so we're going to go ahead and use this. This is bounded by a equals 0 and b equals 1. B equals 1, right? We can kind of see that as well here. But we can also see it in this graph, right? 0 to 1. And then we also have it here, a perfect visualization, right? Here's the rectangle, right? That's the distance from the rectangle to the axis of rotation. The height of the rectangle is the graph that was given to us. And so all you have to do is plug it in. So here's my x. Here's my h of x. Of course, we have to put parentheses because it is one function, right? It's one quantity. And we're going to go from 0 to 1, right? That's where your delta x is being bounded by. So therefore, what we're gonna go ahead and integrate, and this one is pretty basic, right? Pretty straightforward. We're just gonna distribute, simplify it, and we just have to use power rule here. So the integral of x squared is x cubed over 3. The integral of x to the 4th is x to the 5th over 5. 2 pi from 0 to 1. Plug in all the ones, right? We're gonna leave this outside. We're gonna put a big parentheses to make sure we distribute that at the end. So for the first one, let's plug it in. So 1/3 over 3 minus 1/5 over 5. Close brackets, big minus. Now let's try the 0. Now let's plug in those in there. So let's plug in 0 cubed over 3 minus 0/5 to the 5th over 5. Of course, this is just going to be 0, right? So we're just going to ignore that part now and just go ahead and work with this. So that's 1/3 over 3 minus 1/5 over 5 times 2 pi. So it equals 2 pi. And then if you find common denominator, which will be the 15, you multiply this by 5 and you multiply this by 3, right? And so we get 5 minus 3 over 15, which is 2 over 15. And then you multiply it by 2 pi, and that gives you 4 pi over 15. So the volume is 4 pi over 15 cubic units. And of course it's cubic because we're talking about volume. So we just found the volume of this solid. So we don't have the actual shape of this, but I hope you guys are able to sort of kind of see that visualize that in your mind. All right. So there you go, right? That's the formula. Of course, we have to consider different types of rotations. If you guys notice, this was a rotation on the y-axis. We can also have rotations on the x-axis, as we did in the other section, right? So let's formalize this, right? The shell method. So to find the volume of a solid of region with the shell method, use one of the formulas below. So one of them is whenever we have a horizontal axis of rotation. So which one is the horizontal? This one right here, right? So if your rotation happens to be like this on the x-axis or on some horizontal, then we're gonna be using this one. If you notice, this one is a little bit different because now our distance from the rotation function is in terms of y. The height is also in terms of y, and your delta y is in terms of y. And so these are going to be the boundaries in your y-axis, right? versus, as we mentioned before, the vertical axis of rotation. Again, this will be whenever you have the rotation happening on the y-axis, right, or on some vertical axis of rotation. Why am I going out of my way to say that you may not have a axis of rotation in the y-axis? Because we could actually have, a problem where the axis of rotation is vertical, but it happens, let's say x equals 4, right? So we're rotating in this axis. It is still vertical, but it's no longer in the y-axis. I hope that kind of makes sense. Nonetheless, that's the case where we have our the functions will be in terms of x. The distance, again, distance of your perspective rectangle to the axis of rotation, and your height, right? And a and b, these are the boundaries of your delta x times 2 pi. And so what I've always noticed is most students will always forget about 2 pi. So they get caught up too much trying to memorize this, right? But they forget about the 2 pi. Anyway, so let's move on to the next example. Let's try another example. In the next example, we're gonna use a rotation on the x-axis, and I'll go out of my way to kind of point out how you can determine which axis of rotation do we have. So, excuse me. Find the volume of the solid formed by revolving the region bounded. So the region is bounded. Which region is bounded by the graph this and the y-axis? So this is the region bounded, right? And it is rotated, right, about the x-axis. So the word about is a clue that's giving us that this is where the rotation happens, right? The rotation happens on the x-axis. So the word about is the keyword to determine which is the axis of rotation. All right, so I went to go ahead and here and I graph this. So of course you can always use a graphing calculator to graph this. It gives you an idea, right? So here is the example, right? So here is they ask us that is revolving region bounded by this function, which is right here, and the y-axis, which is this is right here. So this is the region being bounded between 0 and 1. Where is y equals 0? Right here. Where is y equals 1? Right here, right? So this, of course, is the region. And we are rotating about the x-axis. So here's my x-axis. We're rotating around here. All right, so again, we're going to rotate here. So we're going to create a shell, right? So a shell, remember, as a shell is, think about it as a cylinder with a hole. Like this, right? And you're going to be adding a bunch of them, right? We're going to be adding a bunch of them. So here we go. So this is the rectangle that we're going to use as a reference. We're going to say that this is my delta y. It's sort of important for us to visualize it because it makes a big difference when we're trying to set it up. So here's my width. Here is the height of my rectangle. And we can say that it's going to be the height of this rectangle is going to be the graph. And then minus 0, right? If you want to kind of say that. And then we need to figure out the distance of our reference rectangle to the axis of rotation. Well, where is the axis of rotation? Right here. So how far is this reference reference rectangle? Well, it's going to be, well, it happens to be that there's no hole right here. They're attached, right? There's no hole right here. So typically then that means that we can just literally just use wherever y is equal to, like for example 3. If that's in there, then y equals 3. So therefore this is equal to your y value. We'll see an example later on where it doesn't, but right now because there's no hole here, you can have a hole. So then therefore it's just going to be y. So there you go. So we have everything. So let's go ahead and try it. So we'll start, we already wrote down the formula we're gonna have, and we're gonna go ahead and jump in and fill it up. So we have 2 pi from what is our p? Our p is y multiplied by y of h, h of y, which is e to the negative y squared dy, and then our y dy is being bounded right in here, right? It's bounded by this, right? So between 0 and 1. All right, so remember these determines your boundaries, right? And then so now let's go ahead and fill it up. So we need to integrate this. So our experience tells us that because we're dealing with an exponential, then most likely we have to use substitution. So the substitution will come in by letting this be u. So we'll say that let's let u equal negative y squared, and then du is going to be negative 2y dy. And then we solve for dy, then this will be dy equals to du over negative 2y. So remember that that's sort of kind of like the way I approach these problems. So we'll replace this with u, and dy we replace it with du over negative 2y. If you notice, this y and this y will cancel each other out. This is a constant, so we'll move it, we'll factor it out, and so therefore we get 2 over negative 2 will give us negative 1 pi from 0 to 1 eu du. And so far we haven't done anything, right? We're just sort of set it up so that we can actually integrate this. Remember that these are in terms of y. So we gotta make sure we keep track of that. So we have negative pi, and then the integral of eu is itself from 0 to 1. But again, these are in terms of y, so we need to rewrite this in terms of y. So that will be negative y squared from 0 to 1. And let's go ahead and plug in our 1 minus the 0. I don't need this bracket. And so we have negative pi. This is going to be negative 1. And this is going to be e to the 0, which is 1. So therefore, we end up getting negative pi 1 over e minus 1. And that's our answer. Or we can just, distribute the negatives. And we can also write it as 1 minus 1 over e. Right? Either one is just fine. And so this is the volume cubic units, right? Because it is a volume. So volume is equal to pi 1 minus 1 over e cubic units. And that's it, right? So if you guys notice, once you have actually the picture, it sort of kind of fits together. It's just easier for us to kind of follow. Very nice. So let's move on to the next problem. Well, the next topic is for us to start discussing, like, what is the benefit between using the shell versus the disk method? Can we use either one? And the answer is yes. But it depends on the problem. So depends on the problem, which one is easier to do, right? And of course, we want to use always the most practical one. So we'll talk about that in a second, but here is an example of the same problem that we just had. But you guys can see the more complicated approach to do this will be to use this method. So if you look at this right here, so this is the same problem. In order for this to be this method, you have to have a bunch of disks, right? And so this is your disk right here. This is your disk. So you have a bunch of disks. The problem with this is that when you're trying to figure out this disk, remember that you have to figure out the height of the radius, or the radius of this, right? Which is no problem here, right? You can find it. You just have to solve this in terms of y, and we're gonna do that in a second. But if you notice that the y value actually changes now from here, right? From here to here, the height of the rectangle is no longer depends on this function, but it actually depends on y equals 1. So we can see here that in order for us to do this with this method, we would have to create a piecewise function and say that the height of y, or y, will be equal to 1 from 0 to 1 over e, and it will be the square root of negative natural log of x from 1 over e to 1. And we would have to actually create two integrals to and add them together to find the volume, right? So we can kind of see that that's really, really complicated, right? It's anytime, if you guys notice, that's one of the hints, is once you have to separate these into two different, regions to be able to satisfy the one of the formulas, then it's not the best approach. And it could happen that the shell method will be the most complicated and that this method will be the best one, right? So we're actually going to talk about that next. So the next topic is how we can compare the both approaches, this method versus the shell method. And of course, at first this is going to be overwhelming, but once you practice a few more, you become more expert, right? You'll be able to pick it up and be able to recognize it by just looking at it and determine which is the best approach. Of course, it's better to visualize it with the picture, but as you move on and you try more problems, you'll be able to do it without graphing it. But for now, let's focus on the graphing. So here is the same problem. We're asked to find the volume of this solid, in this case rotated in the y-axis. And if you notice, that same thing is over here, right? So these two are the same problems, right? They're rotating the same part. And then this one is rotating on the x-axis, so that's sort of similar to this one. So we're going to compare those two approaches. So in this example here, in this approach, we're going to be using we have a vertical axis of revolution, and we're going to use this method. In order for us to use this method, we have to create disks, right? And this disk will be created by rotating it here. So if you guys think about it, this is creating this method, right? And so what do we need for this method? We need two things. We need the big radius and the small radius, right? And that gives us the volume of the cylinder, right? This is in terms of the width of this rectangle is delta y. And this delta y will be bounded between C and D. Between C and D. So notice here that we don't have to figure out where is this distance, right? We don't have to do that for this one. And if you notice here, this method is pi instead of 2 pi. So let's jump in over here. Let's move on to this one. Let's say we approach this using the shell method. We can, yeah, right. We can, right? So we can do that. So on the shell method, we are rotating in this vertical axis. So we're going to create shells, right? We're going to create shells. So if you notice, this is the shell. This is a shell, right? So if you notice that the respective perspective rectangle, if you notice, this one is horizontal. This one is going to be in this case vertical, right? So our width of this rectangle will be delta x. The height of this rectangle, right, will be our h, which is so this one's a little bit um, the height of this will be our h, and then our p will be the distance from this respective rectangle to the axis of rotation, which in this case would just be p. Then we'll multiply by 2 pi outside, and the boundaries of delta x, it will be between a and b. So if you notice, the difference between those two is one of them is laying down, the other one is standing up. So that's very interesting. We're gonna see a pattern going on. Actually here, right? If you notice, when you're doing this method, the disk, if you notice, the disk is perpendicular to the axis of rotation. Notice that disk, your perspective rectangle, is perpendicular to the axis of rotation. Let's see what happens over here. Here's your axis of rotation. What is the representative rectangle is parallel to the axis of rotation. So let's see what happens in the next one. So let's try now. Let's change the axis of rotation. Now it's going to be this one and this one, right? So in the first one, we're going to see almost the same thing, right? Same argument. We're going to have a rectangle here, right? This is the area that we're trying to find. So the radius will be the big radius minus the small radius, and then times your delta x, right? So r squared and r squared, right? And then the boundaries of dx is going to be between a and b. And then we're going to follow up with pi, multiplying by pi. And then so that's our this method. Now let's try the shell method. The shell method, here's the axis of rotation. We need to create sort of cylinders, right? With shells, like shells. So here we go. So it kind of looks like this, right? So the rectangle is going to be laying down. Your delta y will be the width. The height of this will be h, and the distance from here to the axis of rotation will be p. And all we gotta do is multiply p and h by dy from c to d, right? What are the boundaries of your delta y? C and d, right? That's how far it's gonna be moving. Right? It's gonna be moving sideways, right? We're gonna be creating all those rectangles, and then multiply by 2 pi. And so if you notice again, where is the axis of rotation? Right here. If you notice, the perspective rectangle is what? Again, perpendicular to the axis of rotation. Versus over here, the perspective rectangle is parallel to the axis of rotation. And that's actually true. Your this method will always be perpendicular to the axis of revolution, and the shell method will always be parallel to the axis of revolution. So I hope that kind of gives you a better understanding, and you're able to set up the problem with a little more confidence, right? Because you can double check that you're doing this correctly. Very nice. So let's move on to example number 3. So we're trying to determine what's the best approach. Can the shell method be better than the this method, or that this method is better than the shell method. And again, like I said before, it just depends on the problem. It depends on the function. It depends on the axis of rotation. All those are very, very important, right? Those are key. So in example number 3, we're gonna approach all 2 cases. Let's see how easy it is to do it one way versus the other way, right? So let's find the volume of the solid formed by revolving the region bounded by the graph. So we have our graph. So the region is bounded. The region, right? The shaded, if you want to say like the shaded region, is bounded by y equals x squared plus 1 and y equals 0. So where's y equals x squared plus 1? So this is your x squared plus 1, right? It's a parabola bounded by y equals 0. So that's your y equals 0 right here. And then bounded by x equals 0. X equals 0 is right here. Bounded by x equals 1, which is right here. So that region enclosed is all this region right here. And lastly, it's about the y-axis. So whereas that means that it's rotating on the y-axis. So here's the y-axis, so its rotations right here. All right, so we're gonna approach this using the disk method, and we'll compare at the end of the day which one was more practical. So for us to do the disk method in this case, right, we need to figure out, right, the rectangle is going to be perpendicular to the axis of rotation, right? You can see how they're perpendicular. But if you notice, when we're trying to determine the height and the radius, right, because we need to know the radius of this one is going to be 1 for the big radius, right? But for the small radius, they both have different ones. So we have to separate it, because this one has a radius that is different than this radius over here. For example, so this radius right here will be r. So you have to solve for r to be able to solve for x to be able to find this radius. So from this function, where's my function? From this function, solve for x, and that gives us, by subtracting 1 and then doing the square root, that gives us this right here. So between 1 and 2, the big radius is 1 and the small radius is square root of y minus 1. For the other region, we're gonna go between y equals 0 and y equals 1. The big radius is going to be 1 and the small radius is going to be 0. So we're going to separate into 2 regions, and here we have it, right? On the first region right here, we're going to go from 0 to 1 for dy, right? For this one, we're going from 0 to 1. The big radius is 1 and the small radius is 0. Everything's square, right? Each one is square. Plus the pi, and then the other one will be big radius is, we're gonna go from 1 to 2, and we're gonna go from 1 big radius minus small radius, big radius square minus small radius square, and we're gonna simplify this and then find the integral. So from here, it's clearly just gonna be 1, right? 1 squared minus 0 squared is 1. From here, we have 1 minus this, which is pretty much the square root and the square will cancel each other out, which gives us minus y plus 1. Plus 1 plus 1 gives us 2 minus y. Now we can take the integral of 1, which is y, from 0 to 1, carry the pi, plus, carry the pi. The integral of 2 is 2y, minus the integral of y is y squared over 2, and then from 1 to 2. Now let's plug in 1 minus 0, right? Here we go, times pi. Don't forget the parentheses, so we can distribute that pi. Followed by the plus, and then we're going to plug in 2 and 2, right? So 2 times 2 minus 2 squared over 2. That's 1 of 1, big minus, close the bracket, big minus, open the bracket, and now try it again with the 1. And then now we have plug in the 1 and the 1, so we have 2 times 1 minus 1 squared over 2. We'll all simplify that. This is going to be 1 minus 0, which is pi. The pi carries here. That's a 4 minus 2 gives us 2 minus 2 minus 1/2. That 2 and that 2 that's left here are going to cancel each other out. All right, so that's why I canceled them right there. This minus and this minus gives you positive 1/2. So positive 1/2 times pi gives you pi over 2. If you want to take a second here, put a pause video, and then you can try that on your own. Verify that this looks good. Pi plus pi over 2, or that you understand my steps. Pi plus pi over 2 is 3 pi over 2, which gives us volume of 3 pi over 2 cubic units. All right, so we have a few problem. The other problem will be now to do it with the shell method. So the shell method, I already have the formula here. We have the same problem, same rotation. In this case, our rectangle is going to be in parallel to the axis of rotation. Here's my delta x. So we're going to go from 0 to 1 on our boundaries, right? 0 to 1. Carry the pi. The axis, the distance of our respective rectangle to the axis of rotation is going to be x, right? There's no change there. And then for our height of this rectangle will just be the graph itself they gave us. So we're going to plug it in. So P is x, h of x is x squared plus 1. Use distribution, which is give us x cubed plus x. Take the integral of that, so we add 1 and then divide it by the same power. Add 1 to the power, divided by the same power, by the new power. Excuse me. Evaluate from 0 to 1. Keep the 2 pi outside. And then now plug in the 1 minus, now plug in the 0. Remember to put brackets. In this case, it won't matter because this is all 0. And then this is 1 over 4 plus 1/2, which gives us 3/4. Times 2 pi is 3 pi over 2, which gives us the same thing, right? So you can decide that. I think we can deduce here that this was much easier for us to compute. It was much easy, and here the numbers were easy, like 0 and 1. But we can assume that if this is a little more complicated, then this would have been the most practical way to do it. All right. So I got another example here that I want to try. This next example is in particular better for us to use this method, and so we're gonna go ahead and try it. So we have a pontoon is to be made in the shape shown below. The pontoon is designed by rotating the graph of y equals 1 minus x squared over 16 between -4 and 4 about the x-axis where x and y are measured in feet. Find the volume. So the rotation happens on the x-axis. So here's the shape there, the solid we're trying to do. If we're trying to mimic this, right, this is 2 feet and 8 feet that was given to us. And they kind of give us the graph right here. And it's going to be between -4 and 4. And we're going to rotate it about the x-axis. So in this case, there is a consistency on if we try to do this with this method, it's pretty straightforward because it is gonna give us a nice disc, right? You already know the height. The height is consistent with what they give us. The bottom, the small radius will be 0, right? In this case, because you're by the axis of rotation, and then and we're gonna integrate from -4 and 4, right? So here's the big radius. So big radius, small radius. Now let me just maybe argue how would this look like if we were doing the shell method. Well, in that case, we would have to actually make a respective rectangle like this, right? Because remember, it has to be parallel to the axis of rotation. Now, the problem with this is that when you're trying to figure out the height of this rectangle, you're using the same graph. You can do it, it's just not as practical, right? I mean, you have to kind of manipulate the height of this by breaking this into half, ignore this part, and then at the end you double it. So you see how that's gonna be really messy. And the problem was because whenever you have the height and the upper bound and the lower bound of it happens to be described with the same graph. That's always the problem. That's always an issue. So anyway, so obviously here this method was the best option, and we executed this by expanding this binomial that gave us this expression. This was 0, so we sort of ignored it. We took the integral of this that gave us x minus x cubed over 24 plus x to the fifth over 1280 from negative 4 and 4. Don't forget the pi. And then plug it in that. Of course, I expect you guys to always fill in when you're in the test to show me the work, right? And so otherwise I would take off points. So here for purposes of time, and if you guys notice my battery is dying, I'm gonna skip that part. That's just pretty much algebra. All right, so we're gonna jump into the last example here, and in the last example we're gonna use the shell method, and we're gonna find the volume of the solid formed by revolving the region bounded. So the region is bounded by what? It's bounded by what? By this function and this function. So this is a cubic function. So if you graph it, this between and this is the top part, and the bottom part of this is y equals 1. And it's bounded by x equals 1. So here's the x equals 1. And that's it, right? Because you don't have to bound it by 0 because it's already bounded by the cross of these two, by meeting those two there. And then if you notice here, this is rotated about, right? The rotation happens on the x-axis. Nonetheless, is the x-axis, if you guys remember, x-axis, x equals 2 is a vertical line. So the rotation is vertical, right? Vertical. So let's go ahead and find the items that we need in order for us to set it up. So here's our graph, right? We're rotating here, not here, but here, right? This is the axis of rotation. So we're gonna use the shell method in this case. Of course, you could have also used, this method, but in this case, we're just gonna go with the shell method. So the shell method, this one's gonna be parallel. The rectangle is gonna be parallel to the axis of rotation, and so the width of this rectangle is gonna be delta x. The height of the rectangle is going to be the function, given function, minus 1. So the given function minus 1. The trick part here is to determine the distance of the perspective rectangle to the axis of rotation. That's the tricky part. Remember that it would be wrong for us to say that it is x. If you say that the distance of the perspective rectangle is x, then what you're saying is you're implying that the rotation happens here, and that's going to give a different type of volume. So that's not the correct way, right? So what we need to do is figure out is what is the distance from here to here. And it's actually not that bad, because all you gotta figure out is if this right here is x, right? If this is x right here, and we know that this is at 2, Well, if this whole thing is 2, right, and you're trying to figure out this distance from here, then all you gotta do is take 2 and remove this piece, right? You take and you remove this piece. So what I'm saying here is if this is 2, then if you remove x, then you're left with this region right here. Well, 2, then that sounds like 2 minus x. And there you go. That's all we need. And we're going to try to finish up this part right here to set it up. So we have 2 pi, and the rectangle is moving from this way, right? From 0, x equals 0, to x equals 1. So that means from here to here. So that tells us that it's going to go from 0 to 1. We already mentioned that p of x is 2 minus x. H of x is going to be x cubed minus plus x plus 1 minus 1 delta x. And let's go ahead and simplify this. 2 pi from 0 to 1. Before we even begin, let's go ahead and make sure that this looks easy to do. So these will cancel each other out. So we'll go ahead and cancel those 2. Distribution here, here, here. For purpose of time, I'm just gonna go ahead and jump that step, but I know you guys can do that. And then obviously here we have to integrate, we just had to do power rule. From 0 to 1. Nice that I'm using 0 and 1. And then now we're just gonna go ahead and plug it in. First, plug in the 4s. I mean the 1s. Big minus. Now let's plug in zeros. Should we even bother writing it? It's zeros, so we shouldn't, but I'll go ahead and write them. There you go. Just so we can kind of do a good practice. All right, so this is 0. So we're gonna just worry about this. And 2 pi, this is minus 1. This is minus 2, minus 1, plus 2, plus minus 0. This will give us 2 pi. This is going to be negative 2 plus 2, right? So this gives us negative 2. Am I missing something? Oh, yes, I did a big mistake. Let me go back here. Big mistake right here. Let me go back. I forgot to, when I added the powers, I didn't even integrate it. That's the whole thing. I didn't even integrate it. That was a big mistake. Right here. I didn't even integrate. I don't know. I think I was rushing and I didn't even integrate. So it will be adding 1 to the power and divided by the new power. Add 1 to the power divided by the new power. Add 1 to the new power divided by the new power. Add 1 to the new to the power divided by new power. All right, so here we go, 2 pi, and let's begin. Negative 1 to the 5th over 5 plus 2 times 1 to the 4th over 4. And here I'm gonna go super fast. 2 times 1 square over 2, and hopefully I don't make another mistake. That's probably the reason why I made a mistake, because I was rushing. I don't like rushing. All right, so this is again all this is all zeros, right? So we can ignore that part now. Negative 1/5 plus 2 over 4, that's 1/2, minus 1/3. This is 1. So we gotta find common denominator. The common denominator looks like is going to be 30. So this will be 6, 15, 10, 30. And this will give us 20, that's positive 20, plus 15, that's 35. 35 minus 6, that's 29. So we'll get 29 times 2 pi over 30. Cancel those, simplify those two by doing 29 pi over 15. So the volume is 29 pi over 15 cubic units. And there you go. All right, so this is the conclusion of 7.3. I hope you guys find this helpful. Please let me know if you guys have any questions. Until next